So I wanted to make a short video talking about growth rates. It's kind of inspired by the COVID-19 cases, and I pulled up this graphic. There's a million of them like that on the web, and what way I want to look at is these dotted lines right here. So these dotted lines represent the cases when the number of infections double every 2 days. Over here, this dotted line, not quite as bad, represents the case when the total number doubles every 3 days. And what I want to derive is a general formula showing first that these represent exponential functions, and to show the general formula of the constant rate of daily increase for cases that double every n number of days. So this is something we're going to be learning very quickly in our class, so it's kind of appropriate we talk about it now. So an exponential function is a function of the form f of x is equal to b to the x, where our input value x is actually the exponent and our base is b, where b is greater than 0, but it's not equal to 1. So let's actually show how this type of constant increase, percentage of increase, leads quickly to an exponential function. So I'm going to define a value, and it's going to be m naught, and that's our number of start cases. And we're further going to suppose that m naught is not equal to 0. Now I'm going to let m1 be the number of cases, total number of cases, after 1 day. So that's going to equal to the number of start cases, which is m naught, plus some percentage of increase times m naught. I'm going to pull out and simplify this. That's equal to m naught times 1 plus p. So that's how many cases we have after 1 day when the rate of increase is p. So let's find out how many cases we have after 2 days. Well, that's going to be represented by m2, and m2 is equal to the number of cases we had at the end of day 1 plus some rate of increase p times that value m1. And again, we're going to simplify that by pulling out the greatest common factor, m1. So m2 is m1 times 1 plus p. But notice what m1 is equal to. m1 is equal to m naught times 1 plus p. So I'm going to replace m1 by this value right here to simplify the m2 case. So m1 is equal to m naught times 1 plus p. That's what my m1 is. And then that's multiplied by 1 plus p, which simplifies to m naught times 1 plus p squared. Interesting. So on day 1, I have the total number of start cases times 1 plus p. At the end of day 2, I have the total number of start cases times 1 plus p squared. Well, let's take this down one more step and see if we can kind of see a pattern and make an inference based upon that pattern. So on day 3, we have the total number of cases at the end of day 2 plus some rate of increase p times m2, which is equal to m2 times 1 plus p when I pull out the greatest common factor But M2 is given by this formula right here. So I'm going to replace M2 with this value right here. So that's equal to the number of start cases times 1 plus P squared times 1 plus P, which is equal to M naught times 1 plus P cubed. Now I'm hoping you can see a pattern. For the day 1 cases, after day 1, it's our number of start cases times 1 plus P, and that's raised to the first power. When it's raised to the first power, we don't put a 1 there. At the end of day 2, we have the number of start cases times 1 plus P squared. At the end of day 3, we have the number of start cases times 1 plus P to the third power. So that leads us to the following pattern, which if we were in another math class, we could prove by induction that this pattern actually holds. So the number of cases at the end of n days is the number of start cases times 1 plus P to the nth value. Now if we just assume that there's always a first case, then we can let M naught be equal to 1, and then the number of cases at the end of n days is equal to 1 plus P to the n. But I can easily change this to a function because it depends upon the value of n. Say, well, that's f of n is equal to 1 plus P raised to the exponent n, where n is some natural number. But since the natural numbers are a subset of the real numbers, we'll go ahead and extend this function so that it has the domain of all real numbers, and we can write the customary f of x is equal to 1 plus P to the xth power. Since P is always positive, then P plus 1 is greater than 1, so this fits the definition of an exponential function. And that's the reason we talk about exponential growth. So let's stop for just a second and let's try to derive, using what we've observed here, the value of P for the number of cases that double over after 2 days. So the number of cases after 2 days is our start case times 1 plus P squared. And we're assuming that that has doubled the number of our start cases. Well, we've assumed that M naught is not equal to 0, so we can divide through both sides by M naught. And that gives me 2 is equal to 1 plus P squared. Now I want the positive value of P, so I'm going to go ahead and take the positive square root of both sides. That's going to give me the square root of 2 is equal to 1 plus P. Now my whole goal was to solve for P, so by subtracting 1 from each side, I get the value of P. Now the square root of 2 is about equal to 1.414, so the square root of 2 minus 1 is about equal to 0.41. And when I multiply that by 100, that gives me a 41% rate of constant increase. So if your caseload doubles every 2 days, then that's a constant rate of daily increase of 41%. Let's see what it is, because there were two different rates that were discussed in the graphic I just showed you. What happens for cases that double every 3 days? Well, again, we have the number of start cases double. And what is the number of cases we have at the end of 3 days? That's m naught times 1 plus p cubed. Again, we've assumed that m naught is not equal to 0, so we can divide through both sides by m naught, and that gives us 2 is equal to 1 plus p cubed. So we will take the cubed root of 2, take the cube root of both sides, and that gives us 1 plus p. So the answer, or the value of p in this particular case, is the cube root of 2 minus 1, and that's equal to p, and that turns out to be about 26% of constant daily increase. I'm hoping you're convinced that the general formula for the amount of constant daily increase over n number of days, in other words, the formula I'm deriving is the rate of constant daily increase when cases double after every n days. And the general formula of that is going to be the nth root of 2 minus 1 is equal to p. And if you actually were to graph this particular formula, in other words, f of n is equal to the nth root of 2 minus 1, you will see, and that's equal to p, you will see as n increases, p decreases. This is a decreasing function. And I actually have that graph for you. It's right here. This is f of x is equal to the nth root of the 2 to the 1 over x minus 1 times 100. So I went ahead and multiplied it by 100. It's the equivalent in GeoGebra to the formula I just showed you. So you see that this is a decreasing function. Right here, this point right here, point A, is on day 3. So it's the case where it describes the event where the number of cases double every 3 days. And the percent is 25.89, almost 26%. Down here at point B represents the case when every 15 days the number of cases double. And that represents 4.73%. And all the way down here at point C, it takes 65 days for our number of cases to double. That's better, right? The longer it takes for your number of days to double, the better you are, the flatter the curve, right? And that corresponds to a constant rate of daily increase of 1.07. So I hope this is informative. I mean, it's rather unfortunate we're doing it in a time of COVID-19, and I'm actually forced to discuss this with you over the video. But you're in a math class right now that you're literally on the cusp of studying the very types of functions that models the type of growth rate of a virus that keeps us in the house. So I hope you enjoyed it, and keep studying.